Hydrogen, the smallest atom, only has one electron. So when we do its electron configuration, we only have to write 1s1. What does this mean? This is where the electron lives. 1 means the first shell, or principal quantum number of 1. So if you are following along on the periodic table, this means it's in the top period. S means this electron lives in an S subshell with a spherical shape and with an azimuthal quantum number of 0. 1 up here means there's just one electron in this S subshell. Here is another way we could represent this electron configuration. I like to call it the inverted pyramid diagram. This diagram shows the energy of the orbitals, and each orbital is represented by a little line. The orbitals that get filled first go on the bottom because, according to Aufbau's principle, the ones that are filled first will have the lowest energy. So a minute ago we wrote 1s1. Here's how we could show it. We're going to put a little spin up electron in the 1s subshell. So that was hydrogen. Well, let's go to the next element on the periodic table. Helium has an atomic number of 2, and if it's neutral, it has 2 electrons. We can see there's room for one more electron in the 1s orbital because every orbital can hold 2 electrons, one spin up and one spin down. And here's how helium's electron configuration would look written out the simple way. Okay, let's look at a bigger neutral element. What is the electron configuration for carbon? Now, here's where we can just follow the periodic table. Read left to right and down, just like a book. Or use the diagonal diagram, whichever suits your preference. We start at the upper left of the periodic table with 1s. The 1s subshell will hold 2 electrons. Then we have to go down to the next line with our book analogy, really period, if you're going to be chemistry speak. And that is the 2s subshell. And just like the 1s subshell, the 2s can hold 2 electrons. Moving to the right, we enter the p block of the periodic table. So we can put electrons in the 2p subshell. And to get to carbon, we just need to put in 2. So the last 2 electrons in carbon are the higher energy electrons. And they are in a infinity sign shaped orbital, or a figure 8 shaped orbital. The 2 electrons in the 2s subshell are in a spherical orbital. And note that as the principal quantum number gets bigger, the orbitals that house the electrons also get bigger. Here is how we would show the electron configuration of carbon on the inverted pyramid diagram. We would start with the lowest energy orbital, which is 1s, and we'd put a spin up and then a spin down electron to fill that orbital. The next highest energy orbital is the 2s, so the next electron is a spin up and the 2s, and we can fill that orbital in with a spin down electron. And then the 2p subshell is just a little bit higher in energy, and there are 3 orbitals in that 2p subshell. So the first electron that goes in there is a spin up, and then the next electron is going to be in another orbital. They like to spread out, and it's also going to be spin up. It does this to follow Hund's rule, which is that if you put an electron in and it has a choice about where to go on the same energy level, it'll always take an empty electron and it'll always have the same spin as the other electrons of the same energy. Electrons like to spread out if they can. The next atom would be nitrogen. So following Hund's rule, the next electron would be in a different orbital with the same spin. So here's how we could write the electron configuration for nitrogen. It just becomes 2p3 instead of 2p2. For our thrilling conclusion, I am going to show you the electron configuration of iron and show you why it is ferromagnetic. In the process of doing that, we will very briefly pass through the electron configuration of every element smaller than iron on our way. How do we do this? Follow the periodic table, or if you want, follow the diagonal diagram. There are 2 spots in the 1s subshell. Then we go down to the second period, or the second line, and we fill in the 2 spots on the S block. Then we jump over to the P block. And there are 6 spaces, and all of them get filled in. So at this point, we have done a electron configuration for neon, if you're following it along at home on your periodic table. So now we jump down to the 3rd period, or the 3rd line, so we write 3. And again, we're on the left, so we're in the S block, and there are again 2 spaces. Now we keep going to the right, and we jump to the 3p subshell, and there are 6 spaces there, corresponding to aluminum first, and ending at argon. Now we jump down to the 4th period, and this is where there's a little funny thing happening. It turns out that the 4s subshell orbital is actually lower in energy than the 3d subshell orbital's energies. So let's just see where we are so far now that we are at 4s. We have some catching up to do in our inverted pyramid. We need to finish out our 2p subshell and fill it with 6 electrons. So we fill it in with a spin down electron in each orbital. The next highest energy orbital is the 3s, and it gets a spin up and a spin down. That takes care of our 3s2. P subshells always have 3 orbitals, and they get filled according to Hund's rule, 1 orbital at a time. All spin up followed by all spin down electrons. And here is where we skip 3d and go straight to 4s. Then we go to 3d. But we're all caught up here. So let's go back here and fill in the rest. It would be 6 electrons in 3d because iron is the 6th over in the D block. So we're going to put a 6 up here and be done. So we need to put 6 electrons in the 3d subshell following Hund's rule. Each orbital gets a spin up electron. There's 5, and we need 1 more, and we're going to cram it in here, and it's going to be spin down. Look at all these unpaired electrons. In iron, all of these 4 unpaired electrons can align their spins to create a magnetic field, and that is why iron is magnetic. And we are done. Oh wait, I'm getting a question from the back. Oh, what if you have a really gigantic element and you need to put electrons in the F subshell? Oh, well, you could write out the periodic table the way it should be written. Look, the lanthanides and actinides, we can crunch them right in the middle of the D block like this. Oh, what if you have a really gigantic element, like maybe one that doesn't even exist as far as we know of yet? Well, you'd write the periodic table like this, maybe. Crazy, huh?
Made with Doodlecast Pro.